Hey there, still on 8.2 equations of planes, and now I'm going to do question 10D on page 451. So we're given the x, y, and z intercepts, and I've written them down here already. And we're asked to find a vector equation and parametric equations for the plane. So remember from our discussion thread, what do we need to find the equation of a plane? Well, we need three non-collinear points, right? Do we have that? Yes, we do, because the x, y, and z axes are all mutually perpendicular, which means we know that points on each of those axes cannot be collinear with each other. So what else do we need to actually write the vector equation of the plane? Well, we need two direction vectors and one position vector that ends in a point on the plane. So any one of these points can be a position vector for the plane, right? Because they're all in the plane. So first thing, let's write these intercepts as points, right? So if it's the x-intercept, then y and z would be 0. If it's the y-intercept, then x and z are 0. And if it's the z-intercept, then x and y are 0. We only need one position vector for the vector equation of a line, so we can choose any one of the three, doesn't matter. I'm going to choose OX, let's call it, using the x-intercept. And so it would be 8, 0, 0 minus 0, 0, 0, which is the position vector 8, 0, 0. And then I need two direction vectors for the line, right, to write the vector equation. So since these points are all in the plane, any vector that starts at one of them and ends at the other would be a direction vector for the plane. So therefore I'm going to go ahead and find, for example, the vector that goes from x-intercept to y-intercept. I'm going to call it xy. And so that would be 0 minus 8, so negative 8, negative 3 minus 0, 0 minus 0. And then I think I'll use yz, the vector that starts at the y-intercept and ends at the z-intercept. And so that would be 0, 3, because 0 minus negative 3, 2. I also could have done xz, right? Doesn't really matter. I could have done yx, zy, zx. All of those would be acceptable direction vectors for the plane, as would be any scalar multiple of those vectors, because they are parallel, and any vector that is parallel to the plane is also a direction vector for the plane, because I can slide vectors parallel to themselves in space. So I have my position vector for the plane, I have my two direction vectors. Now I just need to put them in to the vector equation of a plane. So starting with my position vector, 8, 0, 0, plus parameter t times my first direction vector, negative 8, negative 3, 0, plus parameter s times my second direction vector, 0, 3, 2. And so that is one possibility for the vector equation of this plane. Now remember, there are infinitely many possibilities, because I could have used a different position vector for the plane, and I could have used a variety of different, in fact, infinitely many different direction vectors for the plane. So this is just one possibility. Now to get the parametric equations, I'm not going to actually bother writing it out, because it's the same as we've done before with lines and planes. You just write the vector r as x, y, z, and then isolate x, y, and z in terms of the first or second or third components of each of these vectors here. So x would be equal to 8 minus 8t plus 0s, but I don't need to write the 0s, and so on. Alright. My next video is going to be on question 17, which is a little bit more challenging, more of a thinking type problem. See you there.